The cosmos is hiding its greatest stories from us. We live under a sky filled with stars, yet the universe's deepest truths remain locked away, posing questions that defy our understanding. This is a journey through 25 of the most perplexing unsolved mysteries in space, where cutting-edge science meets profound wonder. By the end, you will glimpse the bizarre and beautiful puzzles that define the very edges of human knowledge. We will confront a signal from the void that has never repeated, and a star that dims in ways no one can fully explain. What do you believe is the universe's most carefully guarded secret? That profound silence from the cosmos leads us directly to our first great puzzle. Enrico Fermi, a brilliant physicist, captured it in a single, devastatingly simple question during a casual lunch conversation in the 1950s. Where is everybody? The logic is compelling. Our galaxy alone contains hundreds of billions of stars. Many of those stars have planets, and a significant fraction of those planets could be Earth-like, orbiting in the habitable zone where liquid water can exist. Given the immense age of the universe, over 13 billion years, there has been more than enough time for intelligent life to arise elsewhere, to develop technology, and to spread across the galaxy. Even at a fraction of light speed, a civilization could colonize the entire Milky Way in a few tens of millions of years, a mere blink in cosmic time. So why do we see no signs of them? No interstellar probes, no radio signals we can understand, no grand engineering projects visible against the stars. The universe appears hauntingly empty and silent. This is the Fermi paradox. To frame this puzzle, scientists use a tool called the Drake equation. It is not a strict formula with one answer, but a way to organize our thinking. It multiplies factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the probability of life emerging, the probability of that life becoming intelligent, the lifespan of a technological civilization, and so on. Plug in optimistic numbers and you get a galaxy teeming with civilizations. Use more conservative estimates and the number can drop to just one us. The equation highlights every point where our ignorance could be hiding the answer. One of the most unsettling ideas born from this paradox is the concept of the Great Filter. This is the notion that somewhere between the emergence of simple chemistry and the rise of a galaxy-spanning civilization, there is a step, a barrier, that is extremely difficult or nearly impossible to pass. The terrifying question is, where is this filter located? Is it behind us? Perhaps the jump from non-living matter to simple, self-replicating life is astronomically rare. If so, we have already passed the filter, and the galaxy might be filled with sterile, beautiful worlds but no neighbors. Or, far more chillingly, is the filter ahead of us? Could it be that almost every civilization that reaches our level of technology inevitably destroys itself shortly after, through war, ecological collapse, or some unforeseen technological catastrophe? In that scenario, our own silence might be a grim omen. Scientists have proposed countless other solutions. The rare Earth hypothesis suggests that while microbial life might be common, the specific, delicate chain of events needed for complex animal life, let alone intelligence, is extraordinarily unlikely. It points to our large moon stabilizing Earth's tilt, our Jupiter acting as a cosmic shield, our plate tectonics, and even our position in the galaxy as a series of fortunate accidents. Others propose that advanced civilizations are out there, but they are simply undetectable to our primitive instruments. Their communication might use technologies we cannot conceive of, like neutrino beams or quantum entanglement. Perhaps they have transitioned to a post-biological state, existing as vast, quiet intelligences within computer networks, with no interest in broadcasting their presence. There is even the zoo hypothesis, the idea that they know we are here, but have chosen to observe us from a distance, following a kind of galactic prime directive, allowing us to develop without interference. The silence is not just an absence of sound, it is a mirror reflecting our own place in the universe back at us with startling clarity. Are we a lonely miracle or simply too young and naive to hear the conversation happening all around us? This profound silence is not the only way the universe keeps its secrets. It also hides the very substance that holds itself together. Look at a spiral galaxy, a magnificent pinwheel of stars, gas, and dust. According to the laws of gravity, the stars on the outer edges of that spiral should orbit much more slowly than the stars near the bright, dense center. Think of our own solar system. Pluto, far out on the fringe, crawls along its orbit compared to Mercury, which whips around the Sun at a blistering pace. But when astronomers measured the speeds of stars in distant galaxies, they found something impossible. The stars on the outer edges were moving just as fast as the ones near the center. The entire galaxy was rotating as if it were a solid disk. The visible mass of stars and gas simply did not provide enough gravity to hold these speeding stars in place. According to everything we know, these galaxies should have flown apart long ago. The only logical conclusion is that there is something else there, something we cannot see. A vast, invisible halo of mass must be enveloping each galaxy, providing the extra gravitational glue. We call this mysterious substance dark matter. It is not merely a small component of the cosmos. It is the dominant architecture, the universe's invisible skeleton. Current measurements tell us that everything you have ever seen, every star, every planet, every person, accounts for less than 5% of the universe's total content. Dark matter makes up about 27%. It does not emit, absorb, or reflect any light. It is completely transparent. We know it exists only because of its gravitational pull on the things we can see. Another stunning piece of evidence comes from a phenomenon called gravitational lensing. Einstein's theory of general relativity tells us that mass bends the fabric of space-time. A massive object, like a galaxy cluster, acts like a cosmic lens, warping the path of light from more distant objects behind it. Astronomers see these distant galaxies stretched and distorted into faint, ghostly arcs of light around the foreground cluster. When they calculate how much mass is needed to create that lensing effect, the number is enormous, far greater than the mass of all the visible stars and hot gas in the cluster. Again, the only explanation is a huge amount of unseen dark matter providing the necessary gravity. So what is it made of? The leading candidate for decades has been a hypothetical particle known as a WIMP. That stands for weakly interacting massive particle. The idea is that these particles are heavy, much heavier than a proton, but they interact with normal matter only through gravity and the weak nuclear force, one of the 4 fundamental forces of nature. This would make them incredibly difficult to detect, passing through our planet and our bodies as if we were not even there. To find them, scientists have built exquisitely sensitive detectors in some of the quietest places on Earth, deep underground in old mines or beneath mountains. These labs are shielded from cosmic rays, and their goal is to catch the incredibly rare moment when a WIMP might bump into the nucleus of an atom in their detector, producing a tiny signal of heat or light. After decades of searching, these detectors have remained silent. We have not found a WIMP. This has led physicists to explore other possibilities. Could dark matter be made of primordial black holes formed in the chaos of the Big Bang? Could it be a new type of neutrino, an action, or something even stranger that rewrites the rules of gravity itself? The hunt continues because without dark matter, our story of the cosmos collapses. It shaped the distribution of galaxies in the early universe. It guided the formation of the first stars. It is the hidden framework upon which the luminous universe is built. We are surrounded by an ocean of darkness, and we are only just beginning to learn how to feel its currents. But the universe's hidden architecture is not the end of its strangeness. An even more mysterious force is at work, one that does not pull the cosmos together but actively tears it apart. In the late 1990s, two independent teams of astronomers made a discovery so shocking it earned them the Nobel Prize. They were observing a specific kind of stellar explosion, a Type 1, a supernova, which acts as a standard candle, a cosmic yardstick of known brightness. By measuring how dim these explosions appeared in very distant galaxies, they could calculate how far away they were and, crucially, how fast the universe was expanding when that light was emitted billions of years ago. Everyone expected to find that the expansion of the universe, which began with the Big Bang, was slowing down over time due to the relentless pull of gravity from all the matter, both dark and visible. The results showed the opposite. The expansion of the universe is not slowing down, it is speeding up. Something is pushing galaxies apart from one another with ever-increasing force. That something is dark energy. Today, our best measurements tell us that dark energy constitutes a staggering 68% of the total energy content of the cosmos. Dark matter makes up 27%. Everything else, every atom, every star, every planet, every one of us, is just the remaining 5%, a mere afterthought in a universe dominated by darkness. So what is this force that overwhelms gravity itself? The leading explanation is the simplest and also the most baffling. It is the cosmological constant, an idea Albert Einstein introduced and later called his greatest blunder. He originally added it to his equations to keep the universe static, a force of repulsion to balance gravity's pull. When Edwin Hubble discovered the universe was actually expanding, Einstein discarded the idea. Now it appears he may have been right for the wrong reason. The cosmological constant represents a fundamental property of empty space itself. According to quantum physics, a vacuum is not truly empty. It is a seething foam of virtual particles popping in and out of existence. This quantum activity could endow empty space with an intrinsic energy, a constant pressure that causes space itself to expand. As the universe grows, more space is created, which means more of this repulsive energy, leading to faster and faster expansion. It is a runaway process with no off switch. Another theory suggests dark energy is not constant at all, but a dynamic field that has changed over time, known as quintessence. This would be a fifth fundamental force, distinct from gravity, electromagnetism, and the strong and weak nuclear forces. It could vary in strength, potentially even changing sign in the distant future. But for now, all our observations point to a relentless, accelerating push. The ultimate fate this implies is profound and chilling. If dark energy continues to dominate, the acceleration will only increase. In tens of billions of years, galaxies outside our local group will be pushed away so fast that their light can no longer reach us. The observable universe will shrink to a small island of stars in an ocean of deepening black. Eventually, even the bonds holding galaxies together will be overcome. Stars will be flung apart, then solar systems, and finally, in a time frame so vast it defies comprehension, the very fabric of space between atomic particles will expand faster than light can bridge it. This is the Big Freeze, or the heat death, a future where the universe becomes an unimaginably vast, cold, and empty void. Its energy spreads so thin that no work can be done, no stars can shine, and no life can exist. It is a fate written into the very vacuum of space, a silent, invisible engine driving every galaxy toward an inevitable and lonely end. The chilling future written by dark energy began with a single, silent moment of creation. But has the cosmos ever broken its silence to speak directly to us? On a warm August evening in 1977, a radio telescope in Delaware, Ohio, known as the Big Ear, was engaged in its routine, patient scan of the sky. It was part of the long-running search for extraterrestrial intelligence project, listening for any pattern in the cosmic static that might betray an artificial origin. The data was printed out line by line on continuous fanfold paper, a string of letters and numbers representing signal strength. The next day, a volunteer astronomer named Jerry Amon was reviewing the printout. His eyes scanned down the columns, and then he saw it, a sequence of characters so powerful and unexpected that he circled it in red pen and wrote a single, emphatic word in the margin. Wow! The signal was a narrowband radio burst precisely at the frequency of 1420 MHz. This is a protected frequency, a quiet channel in the radio spectrum where earthly transmissions are forbidden, right near the natural emission line of hydrogen, the most common element in the universe. It was a logical place to send or listen for a cosmic hello. The signal lasted for exactly 72 seconds, the precise duration it would take for a fixed telescope like the Big Ear to scan a single point in the sky. It rose in intensity and then faded away perfectly, like someone turning a cosmic beacon directly toward Earth and then slowly panning it away. The alphanumeric code on the printout, 6 letters and numbers, translated to a signal strength of 30 sigma, an off-the-charts intensity that dwarfed the background noise. It appeared to come from a region near the star Chi Sagittarii, in the constellation Sagittarius, toward the crowded center of our Milky Way galaxy. The discovery sparked immediate excitement and a decades-long hunt. If this was a greeting from another civilization, it should repeat. Teams pointed every available telescope, from the massive Very Large Array to dedicated SETI installations, back toward that patch of sky. They listened for thousands of hours across a wide range of frequencies. The result was absolute, unwavering silence. The wow signal never returned. This one-time nature is the core of its mystery. Natural cosmic events like a stellar flare or a comet should be repeatable or leave other traces. Scientists have rigorously tested every plausible explanation. Could it have been a reflection of a human satellite signal off a piece of space debris? The specific frequency was forbidden for earthly use, and no known satellite matched its profile. Was it a passing comet? Detailed analysis of celestial records showed no comets were in that exact part of the sky at that time. The signal's narrowband character rules out most known astrophysical phenomena like pulsars or black hole emissions, which typically broadcast across a wide range of frequencies. It was a pure, clean tone, exactly what theorists predicted an intelligent transmission would look like. So we are left with a haunting possibility. For 72 seconds in 1977, Earth may have been in the beam of an interstellar lighthouse, a message not meant for us specifically, but one we briefly drifted through. Perhaps it was a targeted broadcast from a civilization that has since gone silent, or a one-time burst from a piece of advanced technology we cannot comprehend. The original printout, with its red circle and that stunned exclamation, remains a testament to a moment when the universe seemed to whisper a secret we were just barely clever enough to hear, but not yet wise enough to understand. It stands alone, a single, perfect question mark etched against the stars. While the wow signal was a singular, enigmatic whisper, the cosmos is also capable of screaming. In 2007, astronomers sifting through archived data from the Parkes Radio Telescope in Australia found something that defied belief. Buried in the recordings was a blast of radio waves so intense, so focused, and so brief it lasted just 5 milliseconds. In that sliver of a moment, it released more energy than our sun puts out in 80 years. This was the first detected fast radio burst, an FRB, a cosmic event of almost unimaginable power and brevity. Since that discovery, hundreds more have been captured, each one a brilliant, fleeting flash in the radio sky. They arrive from all directions, seemingly random, and pinpointing their source is like trying to locate a specific camera flash in a city during a thunderstorm while blinking. The challenge is immense. These bursts are over in a heartbeat, leaving only a faint, dispersive echo in telescope data. For years, their origins were a complete mystery, sparking wild speculation. Could they be the death cries of evaporating black holes? The violent snapping of cosmic strings, hypothetical defects in the fabric of space-time, or, most controversially, could they be evidence of unimaginably advanced technology, like power beams for interstellar light sails propelling spacecraft across the galaxy? The scientific search, however, has begun to yield answers, and they are just as astonishing. A major breakthrough came with the discovery of repeating FRBs. While most bursts are one-off events, a few sources have been heard from again and again, firing off multiple millisecond screams over days, months, or even years. This repetition ruled out any cataclysmic, one-time destruction of an object. You cannot blow up the same star twice. The focus then turned to magnetars, a type of neutron star with a magnetic field so powerful it could strip the information from a credit card from 500,000 miles away. These stellar corpses are known for their erratic, high-energy outbursts. In 2020, astronomers caught a magnetar within our own galaxy producing a radio burst that, while weaker, had all the hallmarks of an FRB. This was a smoking gun, proving that at least some of these cosmic screams come from these incredibly dense magnetic monsters. Perhaps their crusts undergo starquakes, or their tangled magnetic fields snap and reconnect, releasing these colossal pulses of energy. But the story grew even richer. By using networks of telescopes across the globe, scientists have managed to localize several non-repeating FRBs to their host galaxies, often billions of light years away. This localization is a triumph of modern astronomy. It involves catching the burst with a wide-field telescope like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, a revolutionary array that looks like a series of half-pipes and scans the entire northern sky every day. Once CHIME provides an initial alert, other observatories around the world swing into action, triangulating the signal to a precise point in a distant galaxy. These localized bursts often come from galaxies that are actively forming stars, the chaotic nurseries where magnetars are born. So the picture forming is one of cosmic adolescence and violence. These millisecond screams are likely the voices of extreme astrophysics, the birth pangs or growing pains of the universe's most magnetic and dense objects. Yet questions remain. Do all FRBs come from magnetars, or are there multiple cosmic culprits? Why do some repeat and others vanish forever? Each brilliant, fleeting pulse is a postcard from a distant, turbulent galaxy, carrying with it not just immense energy, but the promise of unraveling one more secret of our chaotic and magnificent universe. Even the smallest deviation can unravel our understanding of the cosmos. As the twin Pioneer 10 and Pioneer 11 spacecraft completed their grand tours of the outer planets and began their endless journeys into interstellar space, scientists tracking their trajectories noticed something peculiar. A tiny, unexpected force seemed to be tugging on them, acting as a constant, gentle brake. This was the Pioneer anomaly, a deceleration so minuscule it was equivalent to a 10 billionth of the gravity you feel standing on Earth, yet it was undeniably there. For decades, this faint whisper of a push defied explanation. It was as if the spacecraft were rolling up an invisible hill, slowing against a headwind that shouldn't exist. The implications were staggering. Could this be a sign of new physics, evidence that our theory of gravity, Einstein's general relativity, needed modification at the vast scales of the solar system? Perhaps it was the gravitational pull of unseen dark matter concentrated near the Sun, or even a subtle flaw in how we understood the fabric of space itself. The scientific community embarked on a painstaking, decades-long detective story. The key clue lay not in deep space, but in the very design of the probes. Pioneer was powered by radioactive plutonium, its heat converted into electricity by thermoelectric generators. That process left a lot of leftover warmth, which the spacecraft radiated away into space as infrared light. Crucially, the probes were asymmetrical. Their main dish antenna, pointed steadfastly back at Earth for communication, also acted as a shield, reflecting a portion of that waste heat forward. Photons, even those of infrared light, carry a tiny amount of momentum. When they bounced off the back of the antenna dish and shot out into space, they gave the spacecraft a minuscule kick in the opposite direction, back toward the Sun. It was a perfect example of thermal radiation pressure, a gentle photon breeze pushing against the craft's sails. After heroic efforts to recover old data tapes and model the complex thermal blueprint of the aging probes, researchers concluded this effect could account for most, if not all, of the anomalous deceleration. The mystery had a mundane yet brilliant solution. The universe wasn't whispering a new law of physics, it was reminding us of an old one we had overlooked in our calculations. Yet, for some scientists, a sliver of the anomaly remains unresolved, a ghost in the data that the thermal models cannot perfectly explain. The story of the Pioneer anomaly is a profound lesson in humility and perseverance. It shows how the cosmos tests us not only with grand, explosive mysteries, but with subtle, persistent nudges. It celebrates the scientists who spent years chasing a signal 1/10,000,000th the strength of gravity, proving that sometimes the smallest questions lead to the deepest understanding of our own creations and the silent laws that govern their flight. But the universe's whispers are not limited to fleeting radio bursts. Sometimes the mystery is written in plain sight, in the steady heartbeat of a star's light. In the constellation Cygnus, about 1,500 light-years away, a star designated Cassi 8462852 began behaving in a way that defied every textbook. Astronomers, using data from the Kepler Space Telescope, noticed its light was dipping in the strangest patterns imaginable. Most stars with planets show regular, gentle dimming as a world transits across their face, like a moth passing in front of a porch light. This star was different. Its light would plummet by enormous amounts, up to 22%, and the dips were chaotic, irregular, and asymmetrical. Some lasted for days, others for weeks, with no predictable rhythm. It was as if something massive, jagged, and utterly opaque was drifting in front of the star in a clumsy, haphazard dance. The strangeness was so profound that it sparked one of the most exciting and controversial hypotheses in modern astronomy. Could this be evidence of an alien megastructure? Specifically, a Dyson swarm. The concept proposed by physicist Freeman Dyson imagines an advanced civilization capturing the vast energy output of its star. They would construct a vast array of solar collectors, satellites, or habitats in a dense cloud around the star, blocking its light in irregular patterns as the swarm rotates and shifts. The idea was not that we were seeing a solid shell, but a partially completed, messy construction project on a stellar scale. For a moment, it felt like we might have stumbled upon the ultimate cosmic engineering project. Of course, scientists immediately raced to find a natural explanation. The first and most popular candidate was a giant swarm of comets, perhaps a family of icy bodies shattered by a collision, was creating a vast, dusty cloud that orbited the star in a highly elliptical path, causing the deep, irregular dimming. Others proposed a recent planetary collision, leaving behind a swirling debris field of pulverized rock and dust. Observations from other telescopes, however, began to chip away at these ideas. Detailed studies of the star's infrared light showed no excess heat, which you would expect from a cloud of warm dust close to the star. It was as if whatever was blocking the light was cold or not there at all in a thermal sense. Further monitoring revealed another layer to the puzzle. Historical data from photographic plates showed the star has also been undergoing a long-term, gradual dimming over the past century, fading by a significant amount. This combination of sharp, deep dips and a slow, century-long fade is exceptionally rare. Natural explanations have struggled to account for both phenomena simultaneously. Could it be an intrinsic property of the star itself, Some have suggested it is recovering from a past cataclysm, like swallowing a planet, and is now surrounded by a clumpy disk of ejected material. Others point to interstellar dust, not from the star's own system, but from a cold, dark cloud our line of sight happens to pass through, though the fine-tuning required for such an effect is statistically unlikely. To this day, Tabby's star, named after astronomer Tabitha Boyajian, who led its initial study, remains an enigma. No single natural explanation fits all the data perfectly, and the alien megastructure hypothesis, while thrilling, lacks any supporting evidence like radio signals or laser pulses. It stands as a testament to a fundamental truth of exploration. Sometimes the most profound discoveries are not answers but better, more bewildering questions. The star's flickering light is a cosmic semaphore, blinking a complex and as yet undeciphered code, reminding us that nature's imagination often far surpasses our own. The strange flickers of distant stars are not the only way the cosmos presents us with riddles. Sometimes the mystery arrives in our own backyard, a silent visitor from the depths between the stars. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted an object moving at breathtaking speed. Its trajectory was not a closed loop around the sun, like every asteroid or comet we had ever seen. It was on a hyperbolic path, a single, sweeping curve that meant it was not from here. It was our first confirmed interstellar visitor, and we named it Oumuamua, a Hawaiian term meaning scout or messenger from the distant past. Its appearance was startling. Based on the way its brightness changed dramatically as it tumbled, astronomers deduced its shape. It was not round like most space rocks worn smooth by eons of collisions. It was elongated, perhaps 10 times as long as it was wide, like a cosmic cigar or a flattened pancake. This extreme shape was unlike any natural object observed in our solar system. Then came another surprise. As it hurtled away from the sun, something was giving it an extra push. Its speed was ever so slightly higher than what could be explained by gravity alone. This is called non-gravitational acceleration. For a comet, this is common, caused by jets of gas and dust erupting from its icy surface as the sun warms it, acting like a natural rocket engine. But Oumuamua showed no signs of this activity. No dusty coma surrounded it, no tail of gas streamed behind it. It was dark, reddish, and utterly silent, yet something was pushing it. The scientific community scrambled for explanations. The leading natural theory proposed it was a hydrogen iceberg. In the cold, dense cores of giant molecular clouds, hydrogen could theoretically freeze solid. A chunk of this exotic ice flung into interstellar space would accelerate exactly as observed. As it neared the sun, the outer layers would sublimate, turning directly from solid to gas, providing the push without creating a visible tail of dust. The problem was that such an object was purely theoretical, and many doubted it could survive the long journey through interstellar space under the harsh glare of starlight. Another idea suggested it was a chunk of frozen nitrogen, perhaps sheared off the surface of a Pluto-like world in a distant solar system. This, too, could explain the acceleration and lack of dust, but required a very specific and violent origin story. The absence of a clear natural answer opened the door to a more speculative, yet scientifically framed hypothesis. Harvard astronomer Avi Loeb famously suggested we should consider the possibility that Oumuamua was a piece of advanced technology, specifically a light sail. A light sail is a proposed method of interstellar travel, using the gentle pressure of sunlight itself for propulsion, much like a boat's sail catches the wind. A thin, lightweight sheet of material, perhaps only a fraction of a millimeter thick, could be pushed by starlight to incredible speeds. If a larger light sail broke apart, a fragment could tumble through space, and its flat, thin geometry could explain the extreme shape and the way it reflected light. The non-gravitational acceleration would then be perfectly explained by radiation pressure from the sun, pushing on this giant, thin shard. Loeb argued that its unusual characteristics warranted serious consideration of an artificial origin, a call to keep our minds open to the extraordinary. Ultimately, Oumuamua sped away, fading from view before we could gather more definitive data. We will never know its true nature for certain. It remains a single, tantalizing data point, a blurry photograph of a passerby from a realm we have only begun to explore. Whether it was an exotic iceberg or a relic of a distant civilization, its brief passage was a profound reminder. We are not isolated. The galaxy is in motion, sending its messengers on random trajectories, and sometimes, if we are watching closely enough, one of them whispers past our door. Our own galaxy is not an island drifting in stillness. It is caught in a vast, silent river, flowing toward an unknown destination. This is the mystery of the Great Attractor, a gravitational anomaly so powerful it is pulling our entire Milky Way, along with hundreds of thousands of other galaxies, toward a specific point in the cosmos. For decades, astronomers mapping the large-scale motion of galaxies noticed something unsettling. While the universe as a whole is expanding, with most galaxies receding from us due to dark energy, our local neighborhood is moving against the tide. We, along with our neighboring Andromeda galaxy and the entire local group, are being drawn toward the constellation Centaurus at a staggering speed of over 600 kilometers per second. Something with the mass of tens of thousands of Milky Ways must be exerting this pull. The problem was, when we looked in that direction, we saw almost nothing. The culprit lay hidden behind the thick, dusty plain of our own galaxy, a region astronomers poetically call the zone of avoidance. This dense band of stars, gas, and dust blocks our visible light view, like trying to see a distant mountain through a blinding blizzard. For years, the Great Attractor was a ghost, felt but not seen, a titanic presence lurking in the cosmic shadows. The breakthrough came with eyes that could see through the storm. Infrared and radio telescopes, which can penetrate the galactic dust, began to peel back the veil. What they revealed was not a single, monstrous object like a supermassive black hole, but something even grander. The Great Attractor is actually the dense core of a colossal supercluster of galaxies, a gravitational focal point in the cosmic web. Our modern understanding places it as the central gravitational anchor of an immense structure we now call the Laniakea supercluster. Laniakea is a Hawaiian word meaning immense heaven, and it is a fitting name. This structure contains over 100,000 galaxies, including our own, all flowing along invisible filaments of dark matter toward the same great basin of attraction. Imagine a vast, sloping valley in the fabric of space-time. The Great Attractor is the deepest part of that valley, and galaxies are like rivers of stars, all streaming down the gravitational slopes toward it. Maps of this cosmic flow are breathtaking, showing elegant streams and tendrils of galaxy motion converging on that hidden point. Yet, even this colossal structure is not the end of the story. Laniakea itself is being pulled, along with other superclusters, toward an even more massive concentration of matter billions of light years away, sometimes called the Shapley Attractor. We are caught in a nested hierarchy of pulls, a cosmic tug-of-war where the Great Attractor is just one major player in a much larger dance, so the mystery has evolved. We have found the source of the pull, but in doing so, we have uncovered the true scale of the universe's architecture. The Great Attractor is no longer a single, unseen monster, but the beating heart of our local continent of galaxies, a reminder that our home is not a static place, but a traveler on a journey whose ultimate destination is written in the invisible threads of gravity and dark matter that bind the cosmos together. Gravity's grand cosmic flows are governed by rules we think we understand, but at the very edge of reality, where gravity meets the quantum world, those rules break down in spectacular fashion. This brings us to one of the most profound theoretical puzzles in all of physics, the black hole information paradox. It asks a deceptively simple question with universe-shattering implications. When something falls into a black hole, is all information about that object truly lost forever? Your existence is a story written in the quantum states of every particle in your body, the specific arrangement of atoms that makes you you. According to the bedrock principles of quantum mechanics, information is never destroyed. It can be scrambled, transformed, or hidden, but it must, in principle, be recoverable. This is a fundamental law of the universe, yet black holes, as described by Einstein's theory of general relativity, present a terrifying problem. Their event horizon is a point of no return, a one-way membrane from which not even light can escape. If you throw a book, a computer, or an entire star into a black hole, general relativity says it is gone, crushed into the singularity, and all the unique information it carried is erased from our universe. For decades, physicists accepted this grim outcome until Stephen Hawking made a revolutionary calculation. He realized that black holes are not completely black. Due to weird quantum effects happening right at the edge of the event horizon, black holes must slowly leak radiation. This Hawking radiation is created when pairs of virtual particles, which constantly flicker in and out of existence in empty space, appear right at the horizon. Normally, these particle-antiparticle pairs annihilate each other instantly. But if one partner falls into the black hole while the other escapes, the escaped particle becomes real, carrying away a tiny bit of the black hole's energy. Over unimaginable eons, this process causes the black hole to evaporate, shrinking until it presumably vanishes in a final flash. Here is the paradox. Hawking's math showed that this escaping radiation is completely random, like thermal static. It carries no information about what originally fell in. So, imagine a black hole forms from a collapsed star made of hydrogen, and another forms from a collection of old computers and books. Both black holes would evaporate, and the final bursts of Hawking radiation from each would be identical, pure randomness. The unique stories of the star and the books are obliterated. Information is destroyed, violating quantum mechanics. This is the paradox, a direct conflict between our two most successful theories of reality. To resolve it, physicists have proposed mind-bending ideas. One leading concept is the holographic principle. It suggests that all the information about everything that falls into a black hole is not lost inside, but is instead encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared across its surface. The three-dimensional interior is a projection of that data, much like a hologram which looks three-dimensional but is stored on a flat, two-dimensional film. When the black hole evaporates, this information on the horizon is somehow transferred to the escaping radiation, scrambled beyond recognition but not destroyed. Another radical proposal is the firewall hypothesis. It argues that to preserve information, the event horizon cannot be the smooth, gentle gateway general relativity describes. Instead, it must be a searing wall of high-energy particles, a literal firewall that incinerates anything crossing it. This would prevent information from falling in the first place, but it violates Einstein's principle that someone crossing the event horizon should feel nothing special, at least until the tidal forces tear them apart much later. The debate is fierce and ongoing, with new ideas like islands in the stream of radiation emerging. This is not just an abstract puzzle about black holes. At its heart, the information paradox is a battle for the soul of physics, a struggle to write a single set of rules that can describe both the force of gravity that shapes galaxies and the quantum weirdness that governs the particles within them. The fate of information determines whether our universe is ultimately predictable and lawful, or if true, irreversible chaos lurks at the heart of its darkest objects. This battle between quantum rules and gravitational fate plays out on the grandest of stages, the afterglow of creation itself. The cosmic microwave background radiation is the oldest light we can see, a snapshot of the infant universe when it was just 380,000 years old, a fading echo of the Big Bang. It paints a nearly perfect picture of uniformity, a testament to a cosmos that expanded with incredible smoothness. Yet, when scientists created exquisitely detailed maps of this ancient light, they found a pattern that sent a chill down the spine of cosmology. It has been nicknamed the axis of evil. The name is deliberately provocative, capturing the profound unease this discovery caused. The cosmic microwave background should be isotropic, meaning it should look the same in all directions, with no preferred axis or special alignment. The universe should have no center and no edge, with no direction more special than any other. But the data revealed a strange, large-scale alignment. The fluctuations in temperature, those tiny hot and cold spots that seeded all future galaxies, seem to be coordinated along a particular plane in space. Even more bizarrely, this apparent axis seems to be aligned to a startling degree with the plane of our own solar system and the direction of the sun's motion through the galaxy. This is akin to discovering that the fossilized footprints of the first life on Earth are mysteriously aligned with the floorboards in your own kitchen. It feels like a cosmic violation, a suggestion that we occupy a privileged place, which every principle of modern cosmology rejects. The immediate and most hopeful explanation is that this is a statistical fluke, a trick of the data. When you look at any complex map, your brain can find patterns that are not really there, like seeing faces in clouds. Scientists have run countless simulations, and while the axis of evil alignment is unusual, it is not completely impossible to occur by random chance. It could simply be a cosmic coincidence, a quirk we happen to notice. Another strong possibility is that it is an artifact, not of the universe but of our own measurement. Perhaps our view is being contaminated. Interstellar dust within our Milky Way, or even the radiation from the galaxy itself, could be imprinting a pattern on the data that we have not perfectly subtracted. It is like trying to hear a faint, distant symphony while standing next to a humming refrigerator. The local noise might be creating a false melody. Teams have worked tirelessly to clean the maps of all known foreground effects, and the anomaly persists, but the concern remains that some unknown local influence is fooling us. If it is neither a fluke nor an artifact, then the implications are staggering. It could mean our universe is not isotropic on the largest scales. It might have a preferred direction, a fundamental asymmetry written into its fabric at birth. Some theorists have proposed it could be a fingerprint from a time before the Big Bang, evidence that our universe collided with another in a multiverse, or that it inherited a spin from some prior state of existence. Others suggest it might point to a flaw in our understanding of dark energy or the inflationary period that smoothed the early cosmos. The axis of evil remains an open wound in cosmological theory. It is a whisper from the ancient light that seems to say we are not just observers of the cosmos, but somehow, inexplicably, aligned with it. Whether it is a profound clue or a monumental mirage, it forces us to question our most basic assumption that the universe, in its grand design, has no favorite direction. The ancient light's strange alignment speaks of a universe with hidden symmetries, but our nearest neighbor holds a secret about a force that has completely vanished. The Moon today is a silent, stark world, lacking a global magnetic field like the one that protects Earth. Yet when Apollo astronauts brought back rocks from its surface, they carried a ghost within them. These ancient lunar samples, some over 3 billion years old, were found to be permanently magnetized. They were tiny fossils capturing the memory of a magnetic field that once flowed around the Moon, a field that by all rights should never have existed. A planetary magnetic field is a shield generated from within, born from what scientists call a dynamo. This requires a churning, molten metallic core, like Earth's outer core of liquid iron. That molten metal moves as the planet rotates, and through a complex process of convection and rotation, it acts like a giant electrical generator, producing a planet-wide magnetic field. The Moon presents a fundamental problem for this model. It is simply too small. Its core is estimated to be only about 500 kilometers across, a tiny fraction of Earth. A body that small should have lost its internal heat and solidified completely billions of years ago, shutting down any dynamo effect. The evidence, however, is etched in stone. The magnetized rocks prove that for nearly 1 billion years after the Moon's formation, a surprisingly strong field enveloped it, perhaps even half as strong as Earth's is today. So how did our small companion power this invisible shield? One compelling theory points to a dramatic childhood. The early solar system was a violent shooting gallery, and the young Moon likely endured a relentless pummeling from massive asteroids. These colossal impacts may have done more than just carve craters. A truly gigantic strike could have rocked the Moon to its very center, stirring its partially molten core like a spoon in a cup. This external jolt could have jump-started the dynamo, providing the motion needed to generate a magnetic field for a time, even if the core was too small to sustain it on its own. It is a picture of a world whose protective field was powered by catastrophe. Another possibility involves the Moon's unique birth. The prevailing giant impact theory says the Moon formed from the debris of a collision between a young Earth and a Mars-sized object named Theia. This would have left the newborn Moon incredibly hot, covered in a global ocean of magma. As that magma ocean slowly crystallized over millions of years, heavy, iron-rich minerals would have sunk to form the core, while lighter minerals floated to form the mantle. This intense global-scale differentiation, this sinking and rising on a planetary scale, could have created turbulent motions in the core capable of driving an early, powerful dynamo. This mechanism would have been a one-time event, a birth cry of magnetism that faded as the Moon cooled and settled. There is also the chance that we misunderstand the lunar core itself. Perhaps it contains lighter, radioactive elements like potassium mixed in with the iron. As these elements decay, they release heat, acting like tiny internal furnaces. This extra energy could have kept the core churning for longer than a simple iron core would allow. Or maybe the dynamo was powered in a completely different way, not by the core's convection alone, but by the gravitational tug of war with Earth. As the Moon's orbit evolved, the changing gravitational forces or precession could have wobbled the solid mantle, which in turn stirred the liquid core beneath. It is a delicate dance of forces where Earth's pull acts as the hand that spins the top. The silent gray face we see in our night sky is a mask. It hides the history of a world that was once alive with internal fire and wrapped in a protective magnetic embrace. The magnetized rocks are silent witnesses to an era of lunar vitality we can scarcely imagine. Their faint magnetic signature is a puzzle that forces us to rethink not just the Moon, but the very ingredients and processes needed to turn a cold rock into a world with a heart and a shield. What other dormant worlds in our solar system, we must wonder, carry the hidden fossils of forces long since spent? The Moon's vanished magnetic shield is a puzzle of a world that once held hidden fire, but on Mars today, a different kind of whisper hints at a possibility that could redefine our place in the cosmos. The Martian atmosphere, thin and cold, occasionally breathes out a gas that should not be there: methane. This simple molecule, just one carbon atom bonded to 4 hydrogen atoms, has become one of the most tantalizing and frustrating mysteries in planetary science. On Earth, the vast majority of atmospheric methane is produced by living things, from microbes in wetlands to the digestive systems of cattle. Its sporadic detection on the red planet raises a thrilling, profound question. Are we seeing a faint signature of Martian biology, or merely the belches of a geologically active yet sterile world? The detections themselves are maddeningly inconsistent. Orbiters like the European Space Agency's Mars Express and India's Mangalyaan have recorded transient plumes of methane from above. On the ground, NASA's Curiosity rover, trundling through Gale Crater, has performed meticulous measurements with its sample analysis at Mars Instrument Suite. Its data shows a background level of methane so low it is almost negligible, but punctuated by sudden, unpredictable spikes where concentrations soar to 10 times the usual level, only to vanish again within weeks. These spikes are like catching the scent of something on a gust of wind, only for the air to go still and scentless once more. The pattern defies easy explanation. If methane were being produced steadily from a large, ongoing process, we would expect to see a more constant, well-mixed presence in the atmosphere. Instead, these brief, localized bursts suggest localized, perhaps intermittent, sources. The biological possibility is what captures the imagination. On Earth, vast communities of microbes called methanogens thrive in places devoid of oxygen, such as deep underground or in the guts of animals. They produce methane as a byproduct of their metabolism. Could similar organisms exist deep beneath the frozen Martian soil, shielded from harsh surface radiation, perhaps tapping into chemical energy from subsurface water and rock? It is a compelling vision. Future missions might one day drill deep enough to find such a subsurface biosphere, a hidden microbial oasis on a seemingly dead world. Artistic concepts envision these hypothetical microbes not as little green men, but as microscopic, hardy survivors in briny pockets of liquid water, their existence betrayed only by the occasional gas bubble that works its way to the surface and into our instruments. Yet, nature is a master chemist, and there are several purely geological ways to make methane on Mars. One leading process is called serpentinization. This occurs when certain iron-rich minerals in volcanic rock, like olivine, come into contact with water. A chemical reaction takes place, producing hydrogen gas, which can then react with carbon dioxide in the presence of a mineral catalyst to form methane. This requires no life at all, just the right rocks and liquid water, both of which we know exist or have existed on Mars. Another possibility involves ancient methane. Billions of years ago, when Mars was warmer and wetter, biological or geological processes could have produced vast amounts of methane that became trapped in icy cage-like structures called clathrates, frozen into the permafrost. Today, occasional landslides or shifts in temperature could release this ancient, stored gas in sudden, sporadic bursts, like opening a long-sealed soda bottle. Pinpointing the source is the monumental challenge. The methane spikes detected by Curiosity are like hearing a faint knock from behind a thick, locked door. We know the sound came from the other side, but we cannot see what made it. Is the source right beneath the rover's wheels or miles away with the gas transported by winds? The upcoming ExoMars rover, equipped with a drill capable of reaching 2 meters down, and future sample return missions are designed to tackle this very puzzle. They will search for more complex organic molecules, the building blocks of life, and analyze isotopic ratios in the methane. The specific mix of carbon isotopes in a methane molecule can serve as a fingerprint. Biological processes on Earth tend to prefer the lighter carbon-12 isotope over the heavier carbon-13. If Martian methane shows a similar light signature, it would be a powerful, though not conclusive, hint toward a biological origin. This is why the methane mystery is not just a chemical curiosity. It is a direct pathway into the most profound question we can ask about another world. The data graphs from rovers showing those sharp, enigmatic peaks against a flat baseline are more than just readings. They are a map to a potential discovery that would shake our understanding of life's tenacity. Every sporadic detection is a clue in a planetary detective story, a story that may ultimately tell us whether we are alone in our solar system, or if Mars, in its silent, frozen way, still holds a secret living breath. Mars holds its secrets in fleeting whispers of gas, but Saturn announces its strangeness with a shape of impossible perfection. At the planet's north pole, a colossal, six-sided jet stream races around a permanent storm, a geometric hurricane so precise it looks engineered. This is the Saturn hexagon, a feature with no equal anywhere else in our solar system, a 2,500-mile wide cloud pattern that has endured for at least 4 decades. The Cassini spacecraft gave us our first breathtaking close-up views, revealing a honey-colored hexagon framing a churning central vortex like a cosmic eye staring out from the ringed giant. The scale is incomprehensible. Each side of the hexagon is wider than the entire Earth, and the jet stream winds scream along its borders at over 300 miles per hour. How can the chaotic, turbulent atmosphere of a gas giant organize itself into such a stark, geometric form? The answer lies not in alien architects, but in the elegant physics of spinning fluids. Scientists have recreated the essence of the hexagon right here on Earth in laboratory tanks. They fill a circular container with water, place a small rotating cylinder at its center to represent Saturn's spinning pole, and then set the entire outer container into a slower rotation. This simulates the difference in rotational speed between Saturn's poles and its lower latitudes. When dye is added to trace the flow, something remarkable happens. Under just the right conditions, the flowing liquid does not form a simple circle. It snaps into a stable polygon with a number of sides depending on the speed difference. A hexagon emerges naturally from the mathematics of shear, the way different layers of a spinning fluid rub against one another. It is a standing wave, a stable pattern etched into the atmosphere itself. This explains the hexagon's astonishing longevity. Unlike a hurricane on Earth, which is a solitary vortex fueled by warm water and eventually dissipates over land, the Saturn hexagon is a self-reinforcing wave pattern in the planet's deep atmosphere. It is not a single storm, but a permanent feature of Saturn's atmospheric circulation, a fingerprint of its internal dynamics. As long as Saturn keeps spinning, the hexagon likely persists. The Cassini mission also revealed that this geometric wonder is not static. It changes color with Saturn's long seasons. A year on Saturn lasts about 29.5 Earth years, so each season lasts over 7 years. As the North Pole emerged from its long winter darkness into spring sunlight, the hexagon's hue shifted from a bluish tint to a golden honey color. Scientists believe this is due to photochemical reactions in the atmosphere, as increased sunlight creates haze particles that give the clouds their warmer tone. The hexagon, therefore, is not just a shape, but a dynamic, living canvas painted by the planet's chemistry and its slow dance around the sun. It stands as a monumental lesson. The universe often achieves what looks like impossible order through simple, universal laws. A shape that seems too perfect to be natural is in fact a signature of Saturn's deep, churning heart, a six-sided whisper written in wind and cloud that tells us the cosmos has a hidden love for geometry. Geometry in Saturn's clouds is a signature of deep physical laws, but a chemical fingerprint in the toxic skies of Venus hints at something far more provocative. In 2020, a team of astronomers made an announcement that sent shockwaves through the scientific community. They had detected traces of phosphine gas in the temperate cloud decks of our sister planet. On Earth, this simple molecule, one phosphorus atom bonded to 3 hydrogen atoms, has a very specific story. While it can be made in tiny amounts by lightning or volcanic activity, the vast, abundant quantities in our atmosphere are almost exclusively the handiwork of life. Anaerobic microbes, organisms that thrive without oxygen, produce it as a metabolic byproduct. Finding it on Venus was like smelling wood smoke on a lifeless, wind-swept plain. The implication was staggering. Could there be microbial life floating high in the Venusian atmosphere? The discovery focused on a layer about 30 to 40 miles above the planet's hellish surface. Here, the conditions are surprisingly Earth-like. The pressure is similar to sea level on our world, and temperatures range between 30 and 200 degrees Fahrenheit, a balmy zone compared to the 900-degree furnace at the surface. The clouds, however, are not made of water. They are a corrosive brew of sulfuric acid droplets. For any Earth-like life, this is a bath of battery acid. Yet, extremophiles on our planet have shown life can persist in astonishingly hostile niches. The idea of aerial biospheres, microbes using unknown biochemistry to survive inside acidic cloud droplets, suddenly seemed less like science fiction and more like a desperate, thrilling possibility. The scientific response was immediate and intense, a rigorous debate that is the very engine of discovery. Other teams reanalyzed the data. Some could not reproduce the signal, suggesting the original detection might have been a misinterpretation of the spectral data, perhaps confused with sulfur dioxide, a common gas in Venus's atmosphere. The original team stood by their findings, refining their analysis and insisting the phosphine signature was real. The debate then shifted to origins. If it is there, how could it be made without life? Venus is volcanically active, and phosphorus-containing rocks erupted from volcanoes could, in theory, be lofted into the clouds and transformed into phosphine through complex chemical reactions. Other proposals involved sunlight or lightning acting on atmospheric chemicals. The problem is that all known abiotic processes on Venus appear far too inefficient to produce the amount of phosphine reportedly observed. They might create a faint whisper, not the shout the data seem to show. This back and forth is not a failure of science, but its greatest strength. It is the process of a mystery being stress-tested, with every assumption challenged. The Venusian phosphine controversy has done something profound. It has ripped Venus from the category of a scorched, dead world and thrust it back into the spotlight as a prime astrobiological target. For decades, Mars has been the darling of the search for life, but now missions are being designed specifically to probe Venus's cloudy mysteries. Proposals range from balloons that would float for months in the temperate zone, sampling the air directly, to orbiters with more powerful spectrometers to map the gas globally. The vision is of a robotic aerobot drifting silently in the yellow haze, its instruments sniffing the air, trying to catch a definitive whiff of that mysterious molecule, and perhaps, just perhaps, the signature of a form of life so alien it has made a home in the clouds of hell. The phosphine signal, whether it stands or falls, has already changed our cosmic perspective. It reminds us that life, if it exists, will not conform to our comfortable expectations. It might not be on a pleasant, rocky world like ours, but clinging to existence in the most unforgiving places, rewriting the rules of what a habitable zone can be. While Venus may hide life in its acidic clouds, Earth's own sky is constantly bombarded by visitors of a far more violent nature. These are the ultra-high-energy cosmic rays, subatomic bullets fired from cosmic accelerators of unimaginable power. When one of these particles, usually a single proton, slams into the top of our atmosphere, it carries more kinetic energy than a major league fastball. To put that in perspective, it is millions of times more energy than we can produce in our most powerful particle collider, the Large Hadron Collider. This is a proton traveling at a hair's width below the speed of light, a speck of matter carrying the punch of a macroscopic object. The collision is catastrophic. That single proton strikes a molecule of nitrogen or oxygen and creates a cascading firework of secondary particles, a vast spreading shower of electrons, muons, and photons that rains down over several square miles. Scientists detect these showers not by seeing the initial particle, but by capturing the aftermath with arrays of sensors spread across deserts or high plains. The mystery is not that they exist, but where on Earth, or rather where in the cosmos, they come from. A particle with that much energy should be a cosmic roadmap. Charged particles like protons are deflected by the magnetic fields that permeate interstellar and intergalactic space. These fields are weak, but over the millions of light years such a particle must travel, the deflection should scramble its path completely. It should arrive at Earth from a random direction, its origin point utterly lost. Yet, when scientists at observatories like the Pierre Auger Observatory in Argentina map the arrival directions of the very highest energy events, they see hints of correlation. There are slight statistical excesses pointing back toward areas outside our galaxy, toward violent, distant engines. The suspects in this cosmic shooting are the usual extreme celestial phenomena. Active galactic nuclei, where supermassive black holes devour matter and blast out jets of plasma, could accelerate particles to these insane energies. The catastrophic mergers of neutron stars, which produce gamma-ray bursts, are another potential source. Some theorists have even proposed the decay of exotic, super-heavy particles left over from the Big Bang. But each candidate has a problem. If they come from active galaxies billions of light-years away, the particles should have been slowed down by a cosmic roadblock, the sea of microwave background radiation that fills the universe. This is the GZK cutoff, a predicted limit to how far such energetic protons can travel. Finding particles beyond this limit would mean their source is relatively close by, within our own galactic neighborhood. But no known source in our vicinity seems powerful enough to be the culprit, so we are left with a paradox. We are being struck by bullets of matter from a hidden gun. The directions they come from are too scrambled to give us a clear shot back to the shooter, and the energy they carry seems to defy how far they could have traveled. It is as if the universe has a secret particle accelerator, one we have not yet found, operating under rules we do not fully understand, and it is occasionally turning its beam directly toward us. Each time one of these rare, ultra-high energy cosmic rays pierces our sky, it is more than a detection. It is a message written in the language of raw force from the most powerful and elusive engines in existence. The universe's particle accelerators operate on scales we can barely fathom, but sometimes its artistry is displayed in structures of shocking, delicate geometry. Far from the chaos of cosmic rays, a dying star has painted its final masterpiece with breathtaking precision. In the constellation Monoceros, about 2,300 light-years away, the red rectangle nebula glows with a deep crimson hue. Its name is perfectly literal. Through the lens of the Hubble Space Telescope, it appears not as a chaotic cloud, but as a near-perfect hollow rectangle of glowing gas with a brilliant central star at its heart. Even more astonishing are the rungs of dust that stretch across its interior, like the skeletal supports of a cosmic ladder or the subtle grain in a piece of fine wood. This is not an abstract painting, it is a real object, a planetary nebula, the final, glowing shroud ejected by a star in its death throes. The process that creates most planetary nebulae is well understood. An aging star puffs off its outer layers, and the intense ultraviolet radiation from the hot stellar core left behind lights up that expanding shell, often producing beautiful, symmetrical shapes like rings or hourglasses. But a perfect rectangle that defies the expectation of a sphere or even a simple bipolar outflow. The secret likely lies in what we cannot see directly at the center. The star, known as HD 44179, is actually a close binary system. Two stars orbit each other in a tight dance, surrounded by a thick, dense torus, a donut of dust and gas. As the primary star shed its atmosphere, this torus acted like a cosmic nozzle, funneling the ejected material into two opposing cones or jets, shooting out above and below the orbital plane. If those jets were steady, we might see a simple hourglass shape, but here the geometry suggests something more complex. The leading theory is that the entire system is precessing, wobbling like a spinning top that is slowing down. As the binary stars wobble, the direction of their jets slowly traces a circle in space. Over centuries, this sweeping motion has painted the hollow, rectangular outline we see, with the sharp corners marking the extreme edges of the precession cone. The exquisite rungs across the rectangle are thought to be shock waves, like sonic booms in space, created as pulses of material ejected during the star's orbital cycle slam into slower-moving gas from earlier eruptions. Each rung is a timestamp, a frozen echo of a stellar heartbeat, creating a ladder that seems to climb toward the nebulous corners. The deep red color itself is a clue, coming not from common hydrogen, but from a rare type of carbon-rich molecule known as polycyclic aromatic hydrocarbons illuminated by the starlight. The red rectangle is therefore a clock, a compass, and a chemical factory all in one. Its precise shape records the slow wobble of a binary star's death. Its orientation tells us the angle of its hidden equatorial disk, and its composition hints at the complex organic chemistry that occurs around dying suns, chemistry that seeds the interstellar medium with the building blocks for future stars and planets. It stands as a stunning reminder that even in stellar death, the universe obeys a hidden order, sculpting chaos into forms of unexpected geometric beauty. Yet even the universe's most beautiful symmetries can be broken, challenging the very rules we thought governed its structure. In the constellation Cetus, a ghostly galaxy drifts through space, a wispy collection of stars so diffuse you can almost see right through it. This is NGC 1052DF2, and it holds a secret that has thrown cosmology into a fierce debate. According to every model we have, a galaxy this size should be held together by a massive halo of dark matter. Without that invisible gravitational glue, its stars should simply fly apart. Yet when astronomers measured the motions of its star clusters, they found them moving surprisingly slowly. The calculations revealed a shocking truth. This galaxy appears to contain little to no dark matter at all. It is a rule breaker, a cosmic rebel that defies the foundational story of how galaxies form. The discovery sent immediate shockwaves through the scientific community. For decades, dark matter was not just a component of galaxies, it was the essential scaffold. The theory said dark matter halos formed first in the early universe, and ordinary, visible matter, the gas and stars, then pooled within those gravitational wells. Finding a sizable galaxy that seemed to lack this dark matter skeleton was like finding a towering skyscraper built without a steel frame, standing defiantly against the wind. It shouldn't be possible. The controversy, however, hinges on a single critical number, distance. To calculate the mass of a galaxy, you need to know how far away it is. The speed of the moving star clusters tells you the mass inside their orbit, but converting that observed speed into actual velocity requires an accurate distance. If the galaxy is closer than we think, those star clusters are moving slower in real terms, meaning less mass is needed to hold them, supporting the no dark matter claim. If it is farther away, the real velocities are higher, requiring more mass, which could include dark matter. The initial study placed NGC 1052DF2 at about 65 million light-years away, a distance that led to the startling conclusion. But other teams, using different methods, have argued it might be much closer, potentially cutting the distance in half. This isn't just a minor tweak, it's a fundamental shift that could completely alter the math and restore dark matter to the galaxy. This debate over megaparsecs is more than academic bickering. It is the rigorous process of science stress testing an extraordinary claim. Both sides have presented compelling evidence, analyzing the brightness of certain stars and the properties of the galaxy's globular clusters. The uncertainty itself is a lesson in how difficult it is to measure the cosmos with perfect precision. Why does this ghostly galaxy matter so much? Because it is a crucial test. If it truly lacks dark matter, it proves that dark matter and visible matter can, under some circumstances, be separated. This could happen through a violent galactic collision, where the dark matter halo of one galaxy is stripped away by the gravity of another, leaving behind a dark matter-free wreck of stars. Finding such an object validates the particle nature of dark matter, showing it can be dynamically parted from regular matter. If, however, further study proves the galaxy does have dark matter after all, it reinforces the standard model and shows our distance measurements still need refinement. Either outcome pushes our understanding forward. The images of NGC 1052DF2 are haunting. It is an ultra-diffuse galaxy, a faint smudge against the black, with none of the spiral arms or dense core we associate with majestic island universes. Its stars are spread so thin they offer little light, and the charts plotting the velocity of its globular clusters show a flat, calm line where there should be a steep curve indicating hidden mass. This faint smudge of starlight has become a battlefield of ideas, a single data point with the power to confirm or complicate our story of the cosmos. It asks us a profound question: are the rules we have written universal, or does the universe, in its infinite creativity, enjoy writing exceptions? A ghostly galaxy challenges the rules of cosmic structure, but our own solar system may be hiding a rule breaker of its own, a phantom planet lurking in the dark. Far beyond the orbit of Neptune, in the frigid realm of the Kuiper Belt, a handful of small, icy worlds are behaving strangely. Their orbits are not randomly scattered. Instead, they appear to be clustered as if shepherded by an unseen hand. Their elongated paths all seem to swing out into space in roughly the same direction, and their orbital planes are tilted in a similar way. This peculiar alignment is statistically very unlikely to happen by chance. The most compelling explanation, proposed by astronomers Konstantin Batygin and Mike Brown, is a massive, undiscovered planet. This hypothetical world, dubbed Planet 9, would be a true giant, perhaps 5 to 10 times the mass of Earth. It would not be a small rock, but a super-Earth or a mini-Neptune, a class of planet common around other stars but conspicuously absent from our own neighborhood. Its orbit would be immense and highly elliptical, taking it on a lonely, millennia-long journey. At its closest approach, it might come within 200 or 300 astronomical units of the Sun, where 1 astronomical unit is the distance from Earth to the Sun. At its farthest point, it could swing out to over 600 or even 1,000 astronomical units into the deep freeze. This is not a planet in the classical sense we grew up with. It is a ghost, a gravitational specter whose presence is inferred only by the subtle tugs it exerts on the distant debris of our solar system. The search for this hidden giant is a monumental challenge, a cosmic game of hide and seek played on the largest possible board. The primary reason it remains undiscovered is its staggering distance and dimness. At such incredible ranges, even a large planet reflects only a tiny, feeble glint of sunlight. Our most powerful telescopes, like Subaru in Hawaii, must scan vast swaths of the already dark sky, looking for a single, slow-moving pixel of light against a backdrop of millions of fixed stars. It is like searching for a single, specific grain of black sand on a moonless beach, using only a flashlight. The planet's enormously long orbital period, estimated at 10 to 20,000 years, means it moves incredibly slowly across our sky. We cannot predict exactly where in its multi-millennial orbit it might be right now. Astronomers have narrowed down possible locations based on the orbits of the clustered Kuiper Belt objects, creating a search zone that is still dauntingly large. They take images of the sky night after night, looking for any dot that shifts its position just slightly against the stationary stars. It is patient, meticulous work, a digital fishing expedition in the deepest ocean. Not everyone is convinced a single planet is the culprit. Some scientists propose an alternative explanation: the collective gravity of many smaller objects. The Kuiper Belt contains a vast population of icy bodies. Perhaps, they argue, the combined gravitational pull of thousands of these smaller worlds, whose total mass could equal that of a planet, is responsible for shepherding the orbits we see. It is a democratic explanation versus a monarchical one. Instead of one king planet, a parliament of smaller worlds governs the outer solar system through their combined influence. Other researchers suggest that the observed clustering might be an observational bias, a trick of the limited data. we have only discovered a small number of these extreme, distant objects. Perhaps as we find more, the apparent alignment will disappear, scattered into a more random pattern. The debate is active and healthy, pushing astronomers to gather more data and refine their models. Whether it is a single hidden world or the whisper of countless small ones, the mystery of the clustered Kuiper belt objects forces us to rewrite the map of our own cosmic backyard. It hints that our solar system story is not fully told, that a major character may still be waiting in the wings, silently tracing its immense, lonely path through the perpetual night. The search for a hidden planet tests our maps of the solar system, but a deeper mystery is etched into the very atoms of the oldest stars. Our cosmic origin story, the Big Bang, is not just a theory of expansion, but a precise recipe for the universe's first elements. In the furnace of the first few minutes, when the entire cosmos was hotter than the core of a star, protons and neutrons fused to form the nuclei of the lightest atoms, hydrogen, helium, and a trace amount of lithium. This process, called Big Bang nucleosynthesis, is one of the pillars of modern cosmology. The calculations are exquisitely detailed, predicting exactly how much of each element should have been created before the expanding universe cooled and froze those primordial abundances in place. For hydrogen and helium, the predictions match what we observe in the oldest, most pristine regions of space with spectacular accuracy. It is a triumph of science. But for the third element, lithium, the story breaks down. The universe seems to have lost its recipe. The problem is stark when you look at the charts. The predicted abundance of lithium-7, the stable isotope produced in the Big Bang, is about 3 times higher than what astronomers actually measure in the atmospheres of ancient stars in the halo of our galaxy. These stars are cosmic fossils formed from nearly pure primordial gas, so they should preserve that original lithium signature. Yet consistently, they show only about 1/3 of the expected amount. It is as if someone went through the early universe and selectively deleted lithium atoms. This discrepancy is known as the cosmic lithium problem, and it is a quiet crisis that hints at a gap in our understanding of the universe's first moments or the life of stars. Scientists are investigating the mystery from 2 opposite directions. The first possibility is that our models of the primordial nuclear furnace are incomplete. Perhaps unknown particles, like certain types of dark matter, were present in those first few minutes and altered the nuclear reaction rates, reducing the lithium yield. Other theories suggest the presence of magnetic fields or even that the constants of nature, like the strength of the nuclear force, might have been slightly different in that extreme environment. These are profound ideas, suggesting we may need new physics to explain the very first chapter of cosmic history. The other major avenue points not to the birth of the elements but to their later life. Maybe the Big Bang did produce the full amount of lithium, but the oldest stars have been destroying it. Stars are not passive containers, they are dynamic engines. In a star's outer layers, lithium is a fragile element. At temperatures above about 2.5 million degrees, it fuses easily and is destroyed. Some models suggest that these ancient stars, over their billions of years of life, could have mixed lithium from their surfaces down into hotter interior layers where it was burned, effectively erasing the primordial record. Other ideas involve pre-stellar processes, where lithium atoms in the gas cloud that formed the star were dragged onto dust grains or destroyed by light from the first galaxies before the star even ignited. Each potential solution has its challenges. New particle physics must not disrupt the perfect agreement we see with hydrogen and helium. Stellar destruction models must explain why all these ancient stars, seemingly different from one another, show the same consistent depletion. The charts plotting predicted versus observed abundances are a silent call to arms, a graphical representation of a fundamental mismatch. They show 3 confident lines for hydrogen and helium landing right on target, and 1 line for lithium, the prediction. sitting conspicuously above the scattered data points of reality. This is not a wild, speculative mystery, but a precise numerical discrepancy. It is a single digit in a cosmic equation that refuses to balance, reminding us that even our most successful stories of creation may still have missing pages. The fragile balance of lithium in ancient stars speaks of subtle errors in our cosmic recipe, but some events in the universe are anything but subtle. They involve the most violent expulsions imaginable. Imagine a monster, a supermassive black hole weighing billions of suns, the very anchor of its galaxy being hurled into the void. This is not science fiction. Astronomers have found evidence of these runaway behemoths, galactic exiles cast out from their thrones. The cause is a collision of unimaginable power. When two galaxies merge, their central supermassive black holes eventually spiral toward each other, locked in a final, fatal dance. As they merge, the event sends powerful ripples through the fabric of space-time, gravitational waves. If these waves are emitted more strongly in one direction, the newborn black hole can recoil in the opposite direction, like a gun kicking back after firing a bullet. In a spectacular cosmic shot, the merged black hole can be kicked clean out of the galactic center, sent flying into intergalactic space at speeds of millions of miles per hour. Detecting such a phantom is a monumental challenge. We cannot see the black hole itself. Instead, we look for the telltale glow of its last meal. If the black hole was actively feeding on gas before its ejection, that swirling, superheated disk of material, called an accretion disk, might be torn away or left trailing behind. What astronomers search for is a brilliant quasar, the signature of a feeding supermassive black hole that is not centered in its host galaxy. They look for a quasar drastically offset from the core, or even one completely disconnected, racing ahead with a trail of glowing gas streaking behind it like a cosmic wake. One famous candidate is a quasar known as 3C186. Hubble images show it over 35,000 light-years from the center of its host galaxy, a distance so vast it strongly suggests a powerful recoil kick sent it flying. Another method involves studying the motion of stars near a galaxy's core. If the stars are orbiting an empty point instead of a concentrated mass, it hints that the gravitational anchor has gone missing. The fate of these runaway giants is a lonely one. They carry with them a retinue of stars that were bound too tightly to its gravity to be left behind, a small, dense cluster of stars doomed to wander the dark between galaxies. Over eons, even this entourage will be stripped away by tidal forces, leaving the black hole utterly alone in the emptiness. Simulations of these events are breathtaking. They show two brilliant dots of light representing the black hole's accretion disks, spinning furiously around each other, their merger sending a visible shudder through the simulated galaxy. Then one luminous dot is seen speeding away, leaving the galactic center dark and quiet. Artistic concepts depict these rogue quasars as brilliant lighthouses adrift in a sea of black, their long, faint trails of gas painting a story of violent exile. These discoveries force us to rethink the life cycle of galaxies. The central black hole is not always a permanent fixture. It can be removed, leaving a galaxy without its heart, potentially altering its future growth and the formation of new stars. The universe, it seems, has a way of evicting its most powerful tenants, sending them on eternal journeys through the silent dark. While rogue black holes wander the voids between galaxies, another kind of emptiness haunts the oldest light of all. Etched into the map of the cosmic microwave background is a chilling anomaly, a vast and profound cold spot that simply should not be there. This is not a tiny blemish. It is a colossal region of space, nearly 1 billion light-years across, where the ancient afterglow of the Big Bang is significantly cooler than the surrounding sky. In a cosmos that is supposed to be uniform on the largest scales, this cold spot is a glaring, enigmatic exception. It is a cosmic bruise, a mark on the infant universe that our best theories struggle to explain. The first and simplest explanation is chance. Perhaps in the grand lottery of quantum fluctuations that seeded the early universe, we just happened to get one exceptionally large cold patch. It is statistically unlikely, like rolling a die and getting the same number a dozen times in a row, but not completely impossible. Scientists have run countless simulations of the universe, and while a cold spot this extreme is rare, it can appear in a handful of their virtual cosmos runs. For many, this is the most conservative answer, a reminder that even in a perfectly standard model, outliers can occur. Yet, the sheer size and chill of the spot push against this comfortable explanation, prompting a search for a physical cause. This leads to a second, more tangible possibility, the supervoid hypothesis. Imagine a vast, nearly empty bubble in the fabric of space, a region where galaxies are strangely scarce. If such a void existed between us and the cold spot, it could theoretically cause the cooling we see through a process called the integrated Sachs-Wolfe effect. As light from the cosmic microwave background travels through the universe, it gains energy falling into gravitational wells like galaxy clusters and loses energy climbing out. In a mostly empty, static universe, these gains and losses cancel out. But in a universe dominated by dark energy, which causes cosmic expansion to accelerate, the gravitational wells themselves evolve as the light passes through. When light crosses a vast, growing void, it loses more energy climbing out than it gained falling in, leaving it cooler and stretched to longer wavelengths by the time it reaches us. It would be like rolling a marble up a hill that is slowly sinking underfoot. The marble loses extra energy in the climb. Astronomers have indeed found a large, sparse region in the direction of the cold spot, but there is a critical problem. The void they have found, while sizable, does not seem nearly large or empty enough to account for the extreme temperature drop. The numbers do not add up. The required void would need to be of such an unprecedented scale that it would itself be a major cosmological mystery. This mismatch keeps the door open to more exotic ideas. The most mind-bending possibility is that the cold spot is a collision scar, a fossil imprint from a time before our universe was even our universe. The theory of cosmic inflation suggests that our entire cosmos underwent a period of hyper-fast expansion in its first fraction of a second, blowing up from a quantum speck to a macroscopic size. This theory also allows for the possibility of a multiverse, where other bubble universes are constantly inflating into existence in a greater meta-cosmos. If, during our own inflation, our budding universe brushed against or collided with another inflating bubble, the energy of that colossal impact could have left a permanent mark on our cosmic microwave background. The cold spot could be the cosmic equivalent of a birthmark from a twin we never knew we had. The debate is fierce because each explanation carries profound implications. If it is a statistical fluke, it reassures us that our standard model is sound, if occasionally quirky. If it is caused by a supervoid, it challenges our understanding of large-scale structure and the distribution of matter. If it is evidence of a multiverse collision, it would be our first empirical hint of realities beyond our own, a crack in the wall of our cosmic isolation. Detailed maps of the cosmic microwave background, when you zoom in on this region, show it clearly, a sprawling, circular area painted in deep blues and purples against the warmer reds and yellows of the rest of the map. It is a quiet, cold eye staring back at us from the dawn of time. Whether it is a cosmic coincidence, a shadow of emptiness, or a bruise from another reality, its very existence is a stubborn question written in the coldest light of creation. Even the orderly clockwork of our solar system has its subtle, persistent tick that does not match our predictions. Mercury, the sun-scorched innermost planet, holds a tiny but critical anomaly in its motion, a whisper that once confirmed Einstein's genius and now might be hinting at something even deeper. Mercury's dance is peculiar from the start. It spins on its axis 3 times for every 2 orbits it completes around the Sun, a stable rhythm known as a 3-to-2 spin-orbit resonance. This means a single day on Mercury from one sunrise to the next lasts 2 of its years, but the planet's entire orbit itself is slowly rotating, a process called precession. Imagine drawing Mercury's elliptical path around the Sun on a sheet of paper. Over centuries, that ellipse itself slowly swivels like a hula hoop turning around a central pole. This precession is very slow but measurable. In the 19th century, astronomers led by Urbain Le Verrier calculated that Newtonian gravity, accounting for the tugs from all the other planets, could not explain the full amount of this orbital swivel. There was an extra 43 arcseconds of precession per century that was unaccounted for, a tiny gap in the math of the heavens. This was the first clue. That missing piece became the first great triumph of Einstein's theory of general relativity. Einstein's revolutionary idea was that gravity is not a mysterious force acting across distance, but the curvature of space-time itself by mass. The Sun's immense mass creates a deep well in this fabric. Mercury, moving so close to the Sun, travels through this severely warped region. Its orbit is not a perfect, static ellipse, but a path that itself slowly rotates as the planet rolls through the curved geometry near the Sun. When Einstein did the calculation, his theory predicted exactly the extra 43 arcseconds per century. It was a stunning confirmation that reshaped physics. Yet the story does not end there. Modern measurements using radar beams bounced off the planet and data from missions like Messenger have become exquisitely precise. They reveal that even after we apply Einstein's corrections and the gravitational pull of every other planet, a minuscule discrepancy remains. It is a whisper within a whisper, an extra fraction of an arcsecond per century that our most complete models cannot yet explain. So what could be causing this nearly imperceptible drift? One possibility brings the mystery back home to Mercury itself. We have long thought of it as a dead, dense ball of iron with a thin crust. But Messenger revealed a planet with a surprisingly rich and complex history, with volatile elements and evidence of a partially molten outer core. If Mercury's core is still dynamically active, or if its shape is slightly more flattened than we assume, the planet's own gravity field could be subtly different. This would affect how it interacts with the Sun's gravity and the gravity of other planets, potentially accounting for that tiny extra precession. It would be a clue written in the planet's hidden geology. Another avenue points back to the Sun. Our star is not a perfect, featureless sphere. It has a slight oblateness, a bulge at its equator caused by its rotation. The gravitational pull from this bulge is incredibly faint, but over millennia, it could influence Mercury's orbit in a way we have not perfectly modeled. Furthermore, the Sun's interior is still mysterious. The precise distribution of mass within it affects its external gravity field. Any error in our solar model could translate into a tiny error in Mercury's predicted path. Then there is the most tantalizing possibility of all. Could this residual precession be a signal of physics beyond Einstein? General relativity has passed every test thrown at it with flying colors, but scientists know it is not the final word. It does not play nicely with quantum mechanics. Some proposed theories of quantum gravity or modified gravity predict subtle deviations in the motion of bodies within strong gravitational fields, effects that would be most noticeable on a planet like Mercury, dancing so close to the solar furnace. Distinguishing between these possibilities is a monumental task of precision. It requires separating an effect smaller than the width of a human hair seen from a mile away from the noise of countless other influences. Future missions with even more precise orbiters or laser-ranging instruments placed on Mercury's surface could provide the data needed. For now, that unaccounted-for fraction of an arcsecond is a quiet hum in the data, a persistent off note in the solar system's harmony. It reminds us that even our greatest theories are approximations, and that the universe always keeps one final secret in reserve, waiting for a more careful measurement, a deeper thought to reveal it. Deep within the eternal ice of Antarctica, a telescope of a most unusual kind is listening for ghosts. The Ice Cube Neutrino Observatory is not a collection of mirrors and lenses, but a cubic kilometer of pristine ice, instrumented with over 5,000 sensitive light detectors buried over a mile beneath the surface. Its quarry is the neutrino, a subatomic wraith so elusive it can pass through a light year of solid lead without a single interaction. Yet, when one of these cosmic phantoms does, on a vanishingly rare occasion, strike an atom in the ice, it creates a faint, telltale flash of blue light. For years, these flashes seemed random, whispers from nowhere. Then, in 2017, IceCube captured a neutrino of such staggering energy that scientists could trace its path back to a point of origin in the distant cosmos. The trail led directly to a blazar, a monster 4 billion light-years away. This was a landmark discovery, the first time a high-energy neutrino had been linked to a specific source outside our galaxy. It opened a new window onto the universe, one that uses not light, but these ghostly particles to spy on its most violent engines. A blazar is an active galaxy with a supermassive black hole at its core, but with a crucial, terrifying orientation. It is pointing one of its relativistic jets, a beam of plasma and radiation moving at nearly the speed of light, directly at Earth. We are staring straight down the barrel of the universe's most powerful particle cannon. The jet is a natural accelerator, hurling protons and other particles to energies far beyond anything we can create. When these ultra-high-energy protons collide with other matter or light within the jet, they can produce not just gamma rays but also neutrinos. The detection meant we had finally found a source for the universe's most energetic neutrinos, and confirmed blazars as cosmic accelerators of unimaginable power. But the story quickly grew more puzzling. The arrival of these ghost particles does not always follow a script. Sometimes a high-energy neutrino detection coincides perfectly with a dramatic flare from the blazar in gamma rays, the highest energy form of light. It is a coordinated cosmic scream, a burst of light and a whisper of a neutrino arriving in tandem, telling a clear story of a sudden, violent event in the jet. Yet, on other occasions, the neutrinos arrive when the blazar appears quiet in gamma rays. The ghost shows up, but the spotlight isn't on. This inconsistency is a profound mystery. It challenges our fundamental models of how these jets work. The leading theory suggests neutrinos are born in the densest, most chaotic regions near the base of the jet, where accelerated protons smash into surrounding gas and light. Gamma rays, however, might be produced in a different part of the jet, perhaps farther out, where the environment is less dense. If this is true, then a neutrino detection without a gamma ray flare could mean we are seeing an outburst hidden deep within the engine, a shudder in the heart of the beast that hasn't yet manifested as a brilliant flash further down the barrel. Alternatively, it could mean our understanding of the particle acceleration process itself is incomplete. Perhaps there are multiple mechanisms at work, or the jet's magnetic fields are even more complex and turbulent than we imagine, sometimes shielding the gamma ray signal or directing it away from us. Every neutrino that IceCube captures from a known blazar is a new piece of a three-dimensional puzzle. Scientists now engage in a practice called multi-messenger astronomy, combining data from neutrinos, gamma rays, X-rays, and optical light to build a complete picture of a single catastrophic event. An alert from IceCube sends telescopes around the world and in space swiveling to stare at a patch of sky, searching for any flicker of light that might correspond to the silent arrival of the ghost particle. The data streams form a symphony of information, with the neutrino playing the deep, subtle bass note that sometimes, but not always, has a matching crescendo of light. This unpredictable dance between the unseen neutrino and the brilliant flare forces us to listen more carefully to the universe's most extreme engines. It suggests that what we see blazing in the heavens is only part of the story, and that the true violence is often communicated first by messengers that travel in perfect silence through anything, arriving from the depths of time and space to melt a few molecules of Antarctic ice, and in doing so, melt our assumptions about how the cosmos operates. Even the most carefully documented experiments can leave behind a flicker of the unexplained. During the Apollo 16 mission in 1972, astronaut John Young performed a simple, beautiful demonstration on the lunar surface. With the camera rolling, he held a geology hammer in one hand and a falcon feather in the other. In the airless void of the moon, where there is no wind resistance, he dropped them simultaneously. They hit the gray dust at the exact same instant, a perfect validation of Galileo's principle that all objects fall at the same rate in a vacuum, regardless of mass. It was a quintessential moment of lunar science, clear and elegant, but if you watch the footage closely, just after the hammer and feather land, something else happens. In the background, a small rock, seemingly independent and several feet away, appears to shudder. It wobbles slightly, then tumbles over. The motion is subtle, but it looks deliberate, almost as if the rock were invisibly tethered to the hammer's impact. For decades, this tiny event has fueled quiet speculation. Could it have been a mere coincidence, a tiny moonquake triggered by the astronauts' movements? The lunar surface is incredibly sensitive. An astronaut's footstep or even the impact of a dropped tool sends vibrations through the ground, seismic waves that travel much more efficiently in the moon's dry, rigid crust than they do on Earth. It is entirely possible that the shock from the hammer hitting the ground, or from Young shifting his weight in his bulky suit, traveled through the regolith and gave that one particular rock just enough of a nudge to tip its delicate balance. Think of it like tapping one end of a table and seeing a salt shaker at the other end tremble. Another straightforward explanation is a simple, natural rock slide. The moon's surface is not a flat table, it is a gentle slope of dust and debris. The rock in question was perched on a small mound. The microscopic settling of dust or a thermal expansion from the sudden sunlight as the lunar day progressed could have been enough to disturb its precarious position. There was no tether, just gravity and instability finally having their way. Yet the timing is what captivates the imagination. The rock's movement occurs so promptly after the hammer's fall that it feels connected, a cosmic domino effect. This has led to more playful, though less likely, speculations. Could a fragment of the hammer or a kicked-up piece of debris have struck it? The video resolution is too low to confirm. Some have even mused, in pure science fiction spirit, about local electromagnetic effects or other unknown lunar properties. The truth is, we will never know for certain. This is the charm of the tethered rock anomaly. It is not a world-shaking mystery, but a small, human-scale puzzle left on another world. It exists because we were there, because an astronaut chose to perform a classic experiment in an extraordinary place, and because a camera happened to be pointing in just the right direction. In the grand catalogue of cosmic enigmas, from dark energy to colliding universes, this one is wonderfully humble. It reminds us that exploration is messy, that even our most controlled moments can generate unexpected questions, and that the moon, for all its silent stillness, still holds a few secrets that wiggle just out of frame. From the silent, drifting rock on the moon to the invisible currents pulling entire superclusters of galaxies, we have journeyed across a spectrum of cosmic bewilderment. These 25 unsolved mysteries are not a catalogue of our ignorance, but a map of our curiosity. They stretch from the grandest scales, where dark energy scripts the fate of all existence and dark matter weaves the unseen architecture of reality, down to the intimate, specific whispers like the 72-second blip of the WOW signal or the erratic flicker of Tabby's star. They encompass the violence of runaway black holes and the delicate geometry of a dying star's final breath. Each puzzle, whether it involves a phantom planet in our solar system or a ghostly particle from a blazar 4 billion light-years away, represents a frontier. They are the unanswered questions that keep astronomers awake at night, that drive engineers to build more sensitive detectors, and that compel us to point our telescopes ever deeper into the past. This is not science failing, it is science working exactly as it should. Every mystery is a door, and humanity's relentless desire to open those doors is what transforms the cosmos from a static painting into an epic, unfolding story. The true wonder is not in having all the answers, but in living in a universe generous enough to keep asking such magnificent questions. It reminds us that the cosmos is far stranger and more wonderful than we can suppose. What mystery will we solve next? Which of these cosmic riddles captures your imagination the most? Let us know in the comments below. And if this journey through the unknown has sparked your curiosity, be sure to like this video and subscribe for more explorations into the deepest wonders of space.